Picture this for a second. You are handed this single massive logistical task. You have exactly 365 days to relocate every single human being currently living on Earth.
Oh, wow. All of them.
Yeah, all 7.4 billion of them. And here's the real catch. You can only use one single unified transportation network to do it.
Right, which sounds like, a theoretical physics problem. Or maybe some thought experiment designed to just completely break a logistics supercomputer.
Exactly, because any infrastructure required to move a planetary population like that it would surely buckle under its own weight, right? But the crazy thing is, it isn't a simulation. It is the real daily operating reality of Indian railways. So welcome to the deep dive.
It's great to be here.
Today, we are immersing ourselves in a massive array of operational data, historical timelines, environmental studies, and engineering blueprints, all to understand the anatomy of one of the world's oldest and most heavily utilized transportation networks.
And it is a genuinely fascinating paradox to analyze because, well, we're looking at a foundational piece of infrastructure that was born in the mid-19th century.
Right, 1850s.
Yeah. And by all traditional metrics of legacy systems, it should be this decaying, inefficient bureaucracy. Yet today, it manages to be simultaneously one of these most technologically ambitious, incredibly cheap, and astonishingly green networks on the globe.
It's wild.
It really defies almost every piece of conventional wisdom we hold about how aging public infrastructure behaves.
It absolutely shatters those assumptions. So, to you listening right now, I want you to just clear your mind of whatever you think you know about old rusting railways or, the inevitable decay of public transit. Prepare yourself for an absolute masterclass in scale, survival, and sustainability.
Let's do it.
Let's jump straight into the sheer physical footprint of this Leviathan, because understanding the scale is really the prerequisite for understanding everything else we're going to talk about today. We're talking about a route length of roughly 68,500 kilometers.
Which firmly positions it as the fourth largest railway network in the world by route length alone. But comparing it purely by route length to, say, the networks in the United States or Russia, it actually masks the true intensity of the operation.
How so?
Well, it is the density of the traffic on those specific 68,000 kilometers that really sets it apart globally. It's not just long, it's incredibly busy.
Exactly, because it's not just empty tracks stretching across some desert somewhere. Those 68,500 kilometers are punctuated by more than 7,300 individual stations.
That is a lot of stops.
Yeah, and on that massive web of steel, they are running around 25,000 trains every single day. Let that number just, sink in for a minute. 25,000 trains.
I mean, that includes everything, right?
Right. Passenger expresses, local suburban commuters, massive freight haulers. It's an entire circulatory system in constant, relentless motion. And that brings us to the staggering human element I mentioned at the top. The projected passenger volume for the 2025 to 2026 period is roughly 741 crore.
And for those of us who operate in billions, that is 7.41 billion passenger journeys.
It is a statistic that almost defies human comprehension.
It really does. Essentially, if you issued a train ticket to nearly every man, woman, and child currently alive on this planet, that represents the sheer volume of traffic this single network processes and executes in one calendar year.
And to make that sheer, physics-defying volume happen, we have to talk about the workforce. Because you don't run 25,000 trains a day across 7,000 stations with a skeleton crew. Here's where it gets really interesting. Indian Railways employs over 1.2 million people.
1.2 million. Consistently ranking it among the largest single employers anywhere in the world.
Yeah, I was trying to contextualize a workforce of 1.2 million for this deep dive, and comparing it to a massive corporation just doesn't do it justice. It is practically military in its scale.
Oh, absolutely.
If you look at the entire active duty personnel of the United States Department of Defense, you are hovering around 1.3 million. So running Indian Railways requires a logistical manpower force comparable to a global military superpower.
That is a crazy comparison, but it's totally accurate.
Right. This isn't just a transport agency. It's a highly coordinated mobile nation. You have track inspectors walking the rails in the dead of night, signal engineers, drivers, station masters, mechanics, caterers. It's a population larger than several small sovereign countries.
Yeah.
And they are all waking up every day with one collective objective, which is to keep the metal moving.
What's fascinating here is that it raises an immediate logistical question. How do you even begin to manage an organization of that size without it just, collapsing into absolute administrative gridlock?
I honestly don't know. How did they...
Well, you simply cannot run a 1.2 million person mobile nation from a single centralized boardroom in New Delhi. The bottlenecks in decision-making would be catastrophic.
Hmm.
So the data shows this brilliant strategy of intense decentralization. They have fractured this mammoth operation down into 18 distinct regional railway zones.
Right, I was mapping out these zones from our sources, and the granularity is intense. You have the massive ones like Northern Railway and Southern Railway, but then it breaks down into East Central, Southeast Central, Northeast Frontier. They have functionally carved the subcontinent into 18 separate operational kingdoms.
And each of those 18 zones acts as a semi-autonomous ecosystem. They have their own general managers, their own massive maintenance hubs, their own administrative headquarters.
So they aren't waiting on the capital for every little thing.
Exactly. By breaking the Leviathan down, they localize the response time. If a monsoon washes out a track in the Northeast Frontier Zone handles it immediately. They don't have to wait for a committee in the capital to approve the repair orders.
That makes a lot of sense. And one of those zones really caught my eye because it isn't just a geographical slice. It is essentially an engineering marvel all on its own. The Konkan Railway. The sources highlight this as a separate corporation altogether. Why did they carve this specific stretch along the western coast out as its own distinct entity?
The Konkan Railway is the perfect case study in how Indian Railways adapts to extreme physical adversity. This is a 738-kilometer stretch hugging the western coast of India, running from just south of Mumbai all the way down to Mangalore.
Okay.
And for decades, the British and subsequent Indian governments deemed it literally impossible to build a railway there.
Impossible why? Was it just the terrain?
The terrain is a complete nightmare for heavy infrastructure. You are dealing with the Western Ghats, which is a massive, incredibly rugged mountain range that basically plummets directly toward the Arabian Sea.
Oh, wow. So you have no flat ground to work with.
None. But it's not just the rock. It's the weather and the geology combined. This region gets slammed by the southwest monsoon every year, receiving up to 4,000 millimeters of rain in just a few months. That creates incredibly unstable laterite soil that is highly, highly prone to massive landslides.
So you're basically trying to lay heavy steel tracks on top of active mudslides.
Precisely. To make it work in the 1990s, when it was finally constructed, they had to bore 91 massive tunnels through solid basalt and soft collapsing earth. And they had to construct over 2,000 bridges to span all the deep valleys and swollen, raging rivers.
Over 2,000 bridges on one road.
Yeah. And because of this unique, highly dangerous, and high-maintenance geography, they structured it as the Konkan Railway Corporation Limited. It's a specialized entity with the specific engineering mandate to tame that coast. It couldn't be managed without a standard flatland railway zone. It required constant specialized geotechnical oversight.
That is just fascinating. And it makes me think about the engineering roots of this entire system because we really have to contrast this incredibly complex modern reality, tunneling through basalt in monsoon season with a workforce of over 1 million with how this whole thing actually started.
The origins are very humble.
Very. The historical timeline in our sources is just wild. Do you know the exact date the very first passenger train ran in India?
It was April 16th, 1853.
1853. We are talking about a time before the American Civil War had even started.
Before the commercial telephone was invented.
Exactly. That very first train ran a route from Bombay, which of course we now know as Mumbai to Thane, and it covered a grand total of 34 kilometers.
34 kilometers.
Yeah. It was hauled by 3 steam locomotives named Sahib, Sindh, and Sultan. 34 kilometers in 1853. And when you compare that humble colonial-era project to today, the contrast is just mind-bending. Our data highlights a specific modern route called the Dibrugarh-Kanyakumari Vivek Express. Have you looked at this one?
Oh, yes. The scale of that route is incredible.
This single train travels over 4,200 kilometers on one continuous journey. It crosses the entire length and breadth of the subcontinent. From a 34-kilometer steam hop to a 4,200-kilometer cross-country odyssey.
And the pivotal moment that allowed that 34-kilometer local experiment to eventually span the entire continent happened roughly a century later. In 1951, Indian Railways was formally nationalized and consolidated.
What was it before that?
Before that, it was a fractured, messy patchwork of dozens of different private, colonial, and princely state railway companies. Many of them were operating on entirely different gauges and with totally different rules. Nationalizing it transformed it into the unified, state-owned circulatory system of the newly independent Indian economy.
Which actually brings up a critical question regarding the engineering choices made back then that still heavily impact the system today. The sources mention that the vast majority of this network runs on something called broad gauge. Now, I know a little bit about global railways, and most of the world, like the US, Europe, China, they use standard gauge.
Right, standard gauge is the global norm.
So why is India running on broad gauge, and what does that actually mean mechanically?
That is a really crucial piece of the engineering puzzle here. Gauge simply refers to the distance between the two parallel rails on the track. Standard gauge, used across most of the world, is 1,435 millimeters wide, so about 4 feet 8.5 inches.
Okay, got it.
But India's broad gauge is significantly wider. It's 1,676 millimeters, or 5 feet 6 inches.
That's a very noticeable difference. Why go that much wider than the rest of the world?
The decision was actually made all the way back in the 1850s by Lord Dalhousie, who was the British Governor-General of India at the time. They anticipated that India would require the movement of incredibly heavy freight over vast distances.
Okay, so a wider track means heavier trains.
Yes, a wider track gauge allows for wider, heavier train cars. But more importantly, it drastically lowers the center of gravity of the train. India is subject to extreme weather, including cyclonic storms and intense monsoon winds. A wider wheelbase provides vastly superior stability against high winds and allows for a higher carrying capacity without the risk of derailing.
Wow.
It was a 19th century decision that inadvertently perfectly positioned them for the massive 21st century passenger and freight loads they handle today.
That is incredible foresight, even if it was driven by, colonial extraction at the time. But that history actually brings up a massive tension in the data we are reviewing. We are talking about a foundational system whose parameters were set 170 years ago.
Yeah, a long time.
By all standard laws of entropy, bureaucratic bloat, and institutional decay. A 19th century concept scaled to this massive size should just become a collapsing, rusting relic. So how do they keep this antique concept not just running, but actually evolving into the 21st century?
That is the absolute core of their survival strategy. The leadership of Indian Railways realized decades ago that sheer scale, without aggressive modernization, is just a recipe for structural collapse. The modernization engine they have built into this network is arguably as impressive as its physical size.
Well, let's dig deep into that modernization engine because the timeline of their technological leaps is fascinating. It's not just about building faster trains. It's about updating the invisible administrative backend that prevents the whole thing from just choking to death.
Administrative tech is usually the unsung hero.
Right. Let's look at 1986. They introduced their first computerized reservation system. I want to try and visualize what was happening before 1986. Think about the logistical nightmare of booking millions of train tickets on paper ledgers. If I'm in a small town in southern India and I want to book a ticket for a train departing from New Delhi next month, how did that even work?
It was an administrative labyrinth. It involved physical telegraphs being sent between stations, massive physical ledgers being cross-referenced by clerks manually, and days or even weeks of delay just to confirm a single seat.
Weeks just for a seat confirmation.
Yeah. It was a system that was fundamentally unscalable. Computerizing the reservation system in 1986 wasn't just like an upgrade. It was the digital salvation of the network. Without it, the physical trains would have kept running, but the passenger access would have completely paralyzed the system.
Right, and they build on that digital foundation continuously. By 2002, the IRCTC, the Indian Railway Catering and Tourism Corporation, launches online ticket booking. Suddenly, the passenger isn't standing in a queue for hours at a station. They are booking from an early internet cafe or their home computer.
Which was revolutionary for accessibility.
Huge. But where the modernization becomes highly visible to the public is the physical hardware, the trains themselves. And recently, this has really kicked into high gear. In 2019, they introduced the Vande Bharat Express. What exactly is the significance of this specific train?
The Vande Bharat represents a major psychological and engineering leap for Indian Railways. Historically, their passenger trains were heavily focused on slow mass transit. The Vande Bharat is their entry into the semi-high-speed category, capable of speeds up to 160 kilometers per hour.
Which is pretty fast for that network.
Very fast.
Yeah.
But its real significance is that it is an entirely indigenous creation. It's an electric multiple unit, meaning there is no separate locomotive pulling the train. The motors are actually distributed throughout the passenger cars, much like a modern subway train.
Oh, interesting. Why do it that way?
This setup allows for incredibly rapid acceleration and deceleration. That is crucial for reducing travel times in a densely populated country where you have frequent stops. It brought aerodynamic design, sealed automatic doors, and modern passenger amenities to the domestic network, all designed and built entirely in India.
And it joins an ecosystem that is already incredibly diverse. I mean, when you look at the types of trains operating on these broad gauge tracks, it is dizzying. We have the new Vande Bharat. But the sources also list the Rajdhani Express, which has historically been the premium overnight connection between the capital and major cities.
Right.
Then you have the Shatabdi for daytime business routes, the Duronto, which are nonstop point-to-point trains, the Garib Rath, which translates to poor man's chariot, offering air-conditioned travel at heavily subsidized rates.
That's a huge mix.
And then the brand new Amrit Bharat Express, standard mail and express trains, and those incredibly crowded suburban local trains in Mumbai and Chennai. It is an entire ecosystem of vastly different vehicular species, all sharing the exact same tracks.
Which highlights a profound operational challenge. Think about it. When you have an aerodynamic Vande Bharat train trying to maintain 160 kilometers per hour, a heavy, slow-moving coal freight train, and a commuter train making stops every 3 minutes, all operating on the same physical infrastructure, the complexity of signaling and scheduling is astronomical.
I can't even imagine the scheduling math.
And at a volume of 25,000 trains a day, the probability of human error becomes a statistical certainty.
Right. If a driver is fatigued, or say if heavy fog obscures a physical red light on the side of the track, disaster is mathematically inevitable.
Exactly, which is precisely why their underlying safety technology had to evolve from visual cues to automated systems.
Okay, let's unpack this, because this brings us to a piece of technology heavily detailed in our sources called the Kavach system, K-A-V-A-C-H. The word translates to armor in Hindi. What exactly is this armor, and how does it actually work on a mechanical level?
Kavach is an indigenous automatic train protection system. To understand how it works, we first have to look at the limitations of traditional rail safety. Traditionally, a train driver looks out the window, sees a green, yellow, or red signal light, and manually adjusts the throttle and brakes.
Right, relying purely on human eyesight.
Yes. But at high speeds or in the dense fog of a North Indian winter, a driver might miss a red light. In railway terms, this is called a CA signal passed at danger. It is the leading cause of catastrophic collisions.
So how does Kavach take human vision out of the equation?
It creates a continuous invisible web of communication between the trains and the tracks. It utilizes RFID radio frequency identification tags embedded securely right between the tracks at regular intervals, usually about 1 kilometer apart, and at all station signals.
Wait, do these tags need power?
No, these aren't powered devices. They are durable, passive tags that simply store location data.
Kind of like a heavy-duty version of the chip in your credit card.
Very similar. As a locomotive equipped with Kavach drives over these tags, a reader under the train powers the tag via an electromagnetic field, reads the exact location data, and feeds it to the train's onboard computer.
Okay.
Simultaneously, the locomotive is equipped with UHF ultra-high-frequency radio antennas on its roof. These antennas are constantly communicating with stationary radio towers placed along the railway line, as well as directly with other trains operating in the same radius.
Okay, so let me make sure I have this right. The train always knows exactly where it is because of the track tags, and it's constantly talking to the broader network via the roof antennas.
Correct.
So what happens when something goes wrong? Walk me through a scenario where a collision is imminent.
Sure. Imagine train A is stopped at a station because of a mechanical issue. The signal behind it is glowing red. Train B is approaching from behind on that exact same track at 100 kilometers per hour. The driver of train B is, say, momentarily distracted or blinded by weather and fails to brake for the red signal. Without Kavach, they plow right into the back of train A.
A total worst-case scenario.
But with Kavach active, as train B approaches the red signal, the RFID tags inform the onboard computer of its exact location and distance to the red light. The UHF radio receives the network status that the signal is red and the track ahead is occupied.
So the computer knows there's a problem even if the driver doesn't.
Exactly. The onboard computer instantly calculates the train's speed, its total weight, and the braking distance required. When the driver fails to initiate braking in time, the Kavach system violently takes over.
It overrides the driver entirely, like it doesn't just suggest they brake.
Completely overrides them. First, it sounds a blaring audio alarm and flashes visual warnings in the cabin. If the driver does not acknowledge and apply the brakes within a few seconds, the Kavach computer automatically cuts the traction power to the motors and aggressively applies the pneumatic air brakes.
Wow.
It will bring a 1,000-ton train to a dead stop before it ever passes that red signal, entirely independent of human input. Furthermore, it automatically broadcasts a distress signal to all other trains in the vicinity, creating this electronic bubble of safety where approaching trains are automatically slowed or stopped.
That is an incredible feat of engineering, and to implement that across 68,500 kilometers of track is just a monumental undertaking. But here is the thing that really stands out to me in these sources. They aren't just importing this tech. They didn't just write a massive check to some European or Japanese engineering firm to come in and install all this, right?
No, self-reliance and indigenous manufacturing are foundational pillars of their operational strategy. Indian Railways is deeply, aggressively, vertically integrated. They don't just operate the network, they build the network and they build the machines that run on it.
And the manufacturing hubs they have established are legendary in their own right. Look at this list from the data. You have the Chittaranjan Locomotive Works in West Bengal, which is one of the largest electric locomotive manufacturers in the world.
Producing hundreds of locos a year.
Yeah. You have the Benares Locomotive Works in Varanasi, the Integral Coach Factory, the ICF down in Chennai, which churns out thousands of passenger coaches every year and was the actual birthplace of the Vande Bharat. Then the Modern Coach Factory in Raebareli and the Rail Coach Factory in Kapurthala. These aren't just assembly plants. They are massive industrial ecosystems, tailoring rolling stock specifically for the extreme conditions of the Indian subcontinent.
It's a massive industrial footprint.
But, I want to push back on this strategy for a moment. Normally, when you see a massive government-run, vertically integrated monopoly where the state owns the tracks, runs the schedules, and builds the trains, it is a recipe for catastrophic bloat, massive inefficiency, and technological stagnation. Why aren't they just acting as an operator and outsourcing the manufacturing to private, specialized giants like Siemens or Alstom, who have been building high-speed rail for decades? Wouldn't that be way faster and more efficient?
It's a very valid critique of government monopolies. And it is true that Indian Railways actually does partner with private entities like Alstom or Siemens for specific, highly specialized projects, like certain high-horsepower freight locomotives.
Oh, so they do use outside help sometimes.
They do. But retaining the bulk of their manufacturing in-house serves a few critical purposes. First, it provides absolute control over their supply chain, which insulates them from global geopolitical shocks. Second, it allows them to iterate designs specifically for Indian constraints, like extreme ambient heat, heavy dust, and the unique structural stress of incredibly high passenger loads, without paying exorbitant licensing fees to foreign firms.
So by building it themselves, they keep the intellectual property and the manufacturing costs brutally low.
Exactly. And that technical sovereignty perfectly sets up what might be the most ambitious technological milestone in our entire source stack. It's projected for 2026. India is launching its first indigenous hydrogen-powered passenger train as part of a localized green transport initiative. Hydrogen trains, developed and built entirely in-house.
Okay, we have to unpack this. I've heard the buzzwords around hydrogen for years, mostly in relation to, experimental cars. But a hydrogen train, how does that actually function on the rails? Are they burning hydrogen gas like a diesel engine burns fuel?
Not at all. It doesn't involve combustion whatsoever. A hydrogen train relies on a device called a hydrogen fuel cell. On the roof of the train, you store compressed hydrogen gas in highly secure tanks. The train also draws in ambient oxygen from the air around it.
Okay, hydrogen and oxygen.
Right. Inside the fuel cell, you introduce the hydrogen gas and the oxygen. A catalyst within the cell causes the hydrogen molecules to split into protons and electrons. The electrons are forced through a circuit, which creates an electrical current. That direct current is then used to drive the electric traction motors that physically turn the wheels of the train.
Wait, so a hydrogen train is actually just an electric train that makes its own electricity on board?
Precisely. It is an electric train that carries its own power plant with it, rather than drawing power from overhead wires. And the real magic of the fuel cell is the chemical byproduct.
What's the exhaust?
Once the electrons complete their circuit, they recombine with the protons and the oxygen. Hydrogen plus oxygen equals H2O. The only exhaust emission that leaves the tailpipe of a hydrogen train is pure water vapor and a little bit of heat.
That is wild. Just water vapor. But wait, if they are electrifying the whole country with overhead wires, which we'll get into shortly, why do they even need hydrogen trains? Where does this specific tech fit in?
It fills a very specific crucial niche. There are certain routes where stringing up heavy overhead electrical wires is either economically unviable or environmentally destructive. Think of the historic narrow-gauge heritage railways winding through the steep Himalayas, like the Kalka-Shimla or the Darjeeling Himalayan Railway.
Right, those really scenic old mountain routes.
Putting massive steel poles and high-voltage wires up there would completely ruin the fragile mountainous terrain and the historical aesthetics. A hydrogen train allows them to completely eliminate dirty diesel on those isolated routes while maintaining the pristine environment, because again, the only emission is water.
Moving from a colonial steam engine spanning 34 kilometers to indigenous hydrogen fuel cells emitting water vapor in just over a century and a half, it's an incredible trajectory.
It really is an engineering triumph.
But hold on. My logical brain is flashing red lights right now. I'm looking at this entire list of achievements. They are developing proprietary automated safety grids like Kavach across 68,000 kilometers. They are designing and manufacturing high-speed aerodynamic trains. They are building hydrogen fuel cell technology from scratch. They are maintaining 7,300 stations and carrying the payroll for 1.2 million employees. Just saying all of that out loud sounds astronomically, mind-bogglingly expensive.
Oh, it is a massively capital-intensive operation, without question. The infrastructure budget is immense.
So logically, if a network is pouring that much capital into cutting-edge tech, R&D, and a massive workforce, the ticket prices must be incredibly high to fund all of this, right? I mean, in every other transit system in the world, the consumer ultimately eats the cost of modernization.
That is a logical assumption in almost any other market, whether it's aviation, private toll roads, or Western rail networks. But this is where Indian Railways flips the script entirely. We are now entering what we might call the affordability paradox.
I am so glad we are diving into this segment because the economic section of these sources is honestly harder to believe than the hydrogen trains. Indian Railways is universally regarded as one of the cheapest modes of long-distance mechanized transportation on the planet. I want to read these numbers slowly so you, listening, can really grasp the scale of this affordability.
The numbers are staggering.
The data states that the approximate passenger cost on Indian Railways is between 0.5 rupees to 2.5 rupees per passenger kilometer.
Let's contextualize what that actually means for a traveler, because those numbers can sound abstract.
Right. So the sources compare this rail cost to other everyday modes of transit in India. Taking a standard bus is going to cost you between 1.5 to 4 rupees per passenger kilometer. Driving a personal car, factoring in fuel and wear, is 4 to 10 rupees per kilometer. And taking a domestic flight ranges anywhere from 5 to 15 rupees or more per kilometer.
So rail is already a fraction of the cost.
A tiny fraction. To put a real-world journey on it, let's say you want to travel 500 kilometers. That is roughly the distance from Boston to Philadelphia or London to Paris. If you take a sleeper class train ticket in India for that 500-kilometer journey, it costs between 350 and 500 rupees.
For a 500-kilometer overnight journey, depending on exchange rates, that is the equivalent of just a few US dollars. It is astonishingly cheap.
And even if you want to travel comfortably, let's say you upgrade to an AC 3-tier train ticket, which means air-conditioned reserved sleeping berths for 500 kilometers. That will cost roughly 900 to 1,500 rupees. Meanwhile, a private air-conditioned bus for the exact same route could run you up to 2,000 rupees, and a flight is going to be 2,500 to 8,000 rupees.
So even the premium tiers remain highly competitive.
Yes, even the upgraded air-conditioned train travel is often dramatically cheaper than flying or taking private buses.
And the contrast is even starker if we zoom out to a global perspective. The economic data ranks India's rail cost level as very low. China is categorized as low to moderate. But when you look at the Shinkansen in Japan, the ICE trains in Germany, or Amtrak in the United States, their passenger costs per kilometer are ranked as high, and the privatized network in the UK is ranked as very high.
Now, I have to play the skeptic here. Usually, in the real world, when something is that dramatically cheaper than its global counterparts, it's because the product is terrible. Is Indian Railways just dirt cheap because it's a completely degraded, low-quality experience compared to Europe or Japan?
It is a fair question, and the sources explicitly address this assumption. They state that this extreme affordability is not a result of a degraded product, but rather a deliberate combination of government macroeconomic policy, sheer economies of scale, and operational cost subsidization.
Okay, so it's a structural thing, not a quality thing.
Right. It is true that Japan and Europe offer faster, more luxurious baseline services, but their exorbitantly higher fares are driven by vastly higher labor costs, different infrastructure funding models that demand immediate profitability, and a complete lack of the specific financial structures India uses to actively suppress ticket prices.
Okay, let's break down the mechanics of those financial structures because the sources list some fascinating reasons for this low cost. Reason number one is something we touched on earlier, which is massive scale. We mentioned the 7.4 billion passenger journeys. How does that volume physically drive the price down?
It comes down to spreading fixed costs. Building a kilometer of railway track, installing the signals, and maintaining the stations costs millions of dollars. That is a fixed cost. It costs the exact same amount of money whether you run one train a day on it or 100 trains a day on it.
Oh, I see.
By running 25,000 trains a day and moving over 7 billion people, the capital cost of the physical infrastructure is sliced into billions of microfractions. The cost per traveler to use that piece of track approaches fractions of a penny. You are witnessing the absolute maximum utilization of an asset.
And it's not just the frequency of the trains, it's the sheer human density inside the trains, high passenger capacity. The data shows that a single Indian Express train can easily carry between 1,200 and 2,000 people. During major holidays or migrations, special festival trains can pack in up to 4,500 people safely.
That is a staggering amount of people in one vehicle.
Think about the math of that. Compare that to a personal car carrying 4 people, a bus carrying 50, or a large passenger plane carrying maybe 350. The volume of human beings you are moving in a single kinetic event mathematically obliterates the per passenger operating cost. The fuel or electricity required to move one train divided by 2,000 people results in a tiny, tiny energy cost per person.
Exactly. The higher the occupancy density, the lower the operational cost per passenger. It's the ultimate physical realization of mass transit efficiency.
But the real secret weapon, the financial mechanism that I found most brilliant in these sources, isn't just about packing people in. The financial model itself is essentially a giant Robin Hood system.
That is a very apt analogy. Explain how the Robin Hood mechanism functions in their accounting.
So the government of India heavily subsidizes passenger fares as a matter of policy. The fares you pay for a sleeper ticket often only recover a portion of what it actually costs the railway to operate that journey. They are actively, deliberately losing money on the everyday passenger.
Which would bankrupt a normal company.
Right. So how do they survive and fund the hydrogen trains in Kavach? The answer is freight. Indian Railways is a colossal logistics company. They transport massive, continent-spanning loads of coal, cement, steel, food grains, petroleum products, fertilizers, automobiles. I mean, if an industry produces it, the railways haul it. And the freight tariffs they charge the industries are actually relatively high. Those freight services generate massive, highly lucrative revenue.
So they take from the wealthy industrial freight sector.
And they give to the passenger sector. They take the massive profit margins generated from hauling thousands of tons of coal and steel, and they use those profits to directly cross-subsidize the everyday citizen's train ticket. The corporate freight shipments are paying a premium so that a university student, a rural farmer, or a large family can travel 500 kilometers across the country for less than the cost of a decent meal.
And if we step back and connect this to the bigger picture, this isn't just a quirky accounting trick to balance a ledger. It is a vital, deliberate macroeconomic strategy by the state. In a vast developing nation like India, affordable transit isn't a luxury. It's an absolute economic lifeline. If you price the rural poor out of the ability to travel, you literally sever them from metropolitan job markets, from superior healthcare facilities, from higher education.
You essentially trap them geographically.
Precisely. By using industrial freight to artificially depress passenger fares, Indian Railways ensures that a lack of purchasing power is not a barrier to physical mobility. It provides a vascular system that connects the most remote, impoverished villages to the booming metropolitan hubs, ensuring that the economic blood of the country continues to circulate to every extremity. It is profound social infrastructure, disguised as transportation infrastructure.
That is such a powerful way to frame it. It's not just a subsidized train ticket. It's a subsidized ticket to the economy itself. And there are other cost-saving measures the sources list that allow them to stretch this money. Centralized management of the network allows for massive bulk purchasing.
which lowers costs significantly.
Yes, and they use standardized rolling stock. Meaning, if they design a passenger coach that works, the ICF in Chennai will build thousands of them exactly the same way. The standardization means maintenance crews across the country only need to learn one system and stock one set of spare parts, drastically reducing maintenance overhead. But there is one specific massive cost saver mentioned in the sources that perfectly bridges the gap to our next major topic.
The transition to electric traction.
Yes. The data points out that electrification significantly reduces operating costs because electric locomotives consume inherently less energy than heavy diesel engines. They have fewer moving parts, so they require far less maintenance, and crucially, they reduce India's massive dependence on importing expensive foreign diesel fuel.
Which is a huge strain on foreign exchange reserves.
Exactly. And that brings us to the biggest, most genuinely shocking aha moment in this entire deep dive, segment 4, the environmental leap.
This is the data point where Indian Railways truly separates itself from almost every other legacy infrastructure project on the planet and where they are setting a global benchmark.
I am going to read the statistics straight from the sources, because when I first read it, I had to stop and verify it 3 times. As of the latest official figures, 99.6% of the broad gauge railway network is electrified. Let me repeat that, 99.6%.
It is an almost incomprehensible logistical achievement when you factor in the sheer scale we discussed in segment 1. We aren't talking about a small transit loop in a single European city here.
No, we are talking about 70,002 kilometers out of a total 70,271 kilometers of broad gauge track. They have methodically strung high-voltage overhead wires across deserts through jungles, over the Western Ghats, and across the Ganges Basin. They only have about 269 route kilometers left to electrify across an entire subcontinent.
Now, to be analytically precise, the sources do clarify that the entire organization is not 100% electric yet.
Where I saw they still retain a fleet of diesel locomotives.
Yes. A tiny fraction of routes still rely on diesel because that final percentage of electrification work is literally ongoing as we speak. More importantly, they retain a strategic reserve of diesel locomotives for emergency backups, for track maintenance work where they have to power down the overhead lines for safety, for shunting, which is the low-speed maneuvering of heavy train cars in and out of sidings and rail yards, and for temporary diversion routes, where a train might be rerouted onto an older, unelectrified branch line due to an accident on the main line.
But effectively, 99.6% of the primary network is functionally a near-total systemic transformation. But I have to admit, when I read this incredible statistic, my skeptical brain kicked in hard. I had a major fundamental pushback.
What was your hesitation?
Well, I thought, wait a minute, I know a bit about India's energy sector. India's electricity grid still relies heavily on massive coal-fired power plants to generate its baseline power.
It does. A very significant portion of India's total electricity generation is currently derived from burning coal.
So if 70% of the electricity grid that is powering these overhead wires is generated by burning coal, isn't the electric train actually just running on coal? How is that saving the environment? Aren't we just engaging in geographic greenwashing? We've just taken the dirty exhaust pipe off the train engine and moved it to a towering smokestack at a power plant 100 miles away. How can we possibly applaud this as a green leap?
That is the absolute perfect pushback, and it is the most common critique leveled at electric vehicles of any kind. It is a completely valid observation about current emissions. But this raises an important question, and this is where the sources introduce a crucial foundational concept that completely shifts how we need to think about infrastructure over a multi-decade timeline. We have to clearly delineate the difference between an electrified railway and a green railway.
Okay, break that distinction down for us. What is the mechanical difference?
An electrified railway simply defines the mechanism of propulsion. It means the trains draw electricity from an external grid to spin their traction motors, instead of burning liquid diesel in a heavy onboard internal combustion engine.
Okay, so it's just about how the train moves.
Right. A green railway, on the other hand, describes the source of that power. It means the electricity feeding that grid comes entirely from renewable, zero-carbon sources, like massive solar farms, wind turbines, or hydroelectric dams.
So to be clear, Indian Railways today is an incredibly massive electrified railway, but it is not fully a green railway yet because of the coal in the national grid.
Correct. But this raises the most important question of the entire deep dive. Why does that intermediate step of electrification matter so much? Why is it worthy of celebration even if the grid is currently dirty? Here is the absolute genius of electrification. Future-proofing.
Future-proofing.
Think of a traditional diesel locomotive. From the day it rolls off the assembly line, its environmental profile is locked in. For its entire 30 or 40-year operational lifespan, it will burn diesel. It will continually spew carbon dioxide, toxic particulate matter, and sulfur dioxide. It is structurally incapable of ever being anything other than a dirty, polluting machine.
Right. It's a closed system.
But an electric locomotive is completely different. An electric train is essentially a blank slate. It's an empty vessel. Its carbon footprint is entirely 100% dependent on the grid it plugs into. Today, yes, a chunk of the electricity flowing into that train comes from coal. But think of it like a smartphone. You don't have to buy a new phone every time your power company upgrades a substation.
Oh, I see where you're going with this.
As India continuously builds out massive solar parks in Rajasthan, as they commission offshore wind turbines in Gujarat, and as they integrate more nuclear and hydropower over the next 20 years, the national grid inherently gets cleaner.
You don't have to rebuild the thousands of trains.
Exactly. This is the brilliance of it. The railway becomes cleaner automatically as the nation's power grid becomes cleaner. You just change the power generation source at the grid level, and instantly, simultaneously, all 25,000 trains running across the country that day become vastly greener, without a single engineer turning a single wrench on the locomotives themselves. A diesel engine is a technological dead end. An electric engine is a seamless bridge to a renewable future.
Okay, that makes perfect logical sense. You build the electric infrastructure now so that when the green power arrives, the trains are already ready to use it. But what about right now? Does an electric train running on a coal grid offer any immediate environmental benefits today, or are we just like waiting for the future?
The localized immediate benefits are actually profound and life-saving. Even if a power plant is burning coal, a massive centralized power plant is thermally vastly more efficient at converting fuel to energy than thousands of tiny vibrating diesel engines scattered across the country. But more importantly, we have to talk about zero tailpipe emissions.
Right, the local air quality. An electric train doesn't produce exhaust smoke.
Exactly. It doesn't pump out PM 2.5 and PM 10. Those are the microscopic particulates from diesel combustion that bypass our biological filters, enter the bloodstream, and absolutely destroy human lungs, leading to asthma, heart disease, and premature death. It produces no localized nitrogen oxides or sulfur dioxide.
Which is huge for cities.
Massive. When you think about incredibly dense Indian metropolitan areas or massive, crowded, semi-enclosed stations like New Delhi or Chhatrapati Shivaji Terminus in Mumbai, replacing thousands of idling diesel engines with silent, exhaust-free electric locomotives drastically lowers the localized toxic particulate matter. It quite literally saves lungs and lives in those immediate urban centers today, regardless of where the power plant is.
And the capacity impact of the railways compounds this environmental benefit on a national scale. The sources state that a single heavy freight train can replace between 100 to 300 heavy trucks on the road.
Let the physics of that sink in. One single electric train removes up to 300 diesel-burning, inefficient, exhaust-spewing heavy transport trucks from the national highway system.
The ripple effects of that are staggering.
No.
That means massively lower national diesel consumption, which means less reliance on imported foreign oil. It means reduced highway congestion, making the roads safer for everyone else. It means vastly less physical wear and tear on the road infrastructure itself, which is vital because repairing roads requires carbon-heavy asphalt and heavy machinery. The overall emissions generated per ton of cargo transported just plummet the moment you move it from rubber tires on a road to steel wheels on an electrified rail.
And when you look at passenger travel, the comparative energy efficiency is unmatched. The sources provide a relative energy efficiency scale calculating the energy required per passenger kilometer. Airplanes, due to the physics of fighting gravity and air resistance at high speeds, are rated as low efficiency. Private cars are moderate. Buses are good. But electric trains are rated as excellent, a full 5 stars.
Really? 5 stars?
Yeah, because the coefficient of friction between a smooth steel wheel and a smooth steel track is incredibly low.
Yeah.
Because of this physical reality, trains require significantly less kinetic energy per passenger to maintain speed than a rubber-tired car on asphalt or an aircraft in the sky.
And what's really impressive is that Indian Railways isn't just resting on the laurels of grid electrification. The data highlights an array of aggressive, localized green initiatives they are implementing right now. They are installing massive arrays of rooftop solar panels on thousands of railway stations and administrative buildings, generating their own localized green power.
Offsetting their station grid usage.
Right. They are actively procuring wind energy from independent producers. They have completely swapped out their old lighting systems for energy-efficient LED lighting across the entire network, every station, every office, every train car. And they utilize a brilliant piece of physics in their electric locomotives called regenerative braking.
Regenerative braking is a fascinating mechanical process. Can you explain how they recover that energy?
Sure. So a 1,000-ton train moving at 100 kilometers per hour possesses a massive amount of kinetic energy. Traditionally, when a train needs to stop, pneumatic brakes clamp down on the wheels. This creates friction, which converts all that valuable kinetic energy into waste heat that just dissipates into the air. It's lost energy.
Just burning it off into the atmosphere.
Exactly. But with regenerative braking on an electric locomotive, when the driver applies the brakes, the electric traction motors that normally drive the wheels are essentially run in reverse. They become electrical generators. The momentum of the heavy train spins the generator, slowing the train down, but instead of creating waste heat, this physical resistance generates fresh electricity.
That is so cool.
Right. That generated electricity is then fed back up through the pantograph on the roof, directly into the overhead wire, where it can be used instantly by another train accelerating a few kilometers down the track. They are literally reclaiming their own momentum to power the network.
It is the ultimate example of maximizing efficiency. And let's not forget the massive biological initiatives detailed in the sources. The railways own vast tracts of land along their 68,000 kilometers of track. They have initiated large-scale tree plantation and water conservation programs along these boundaries. They're utilizing their massive land holdings to act as a continental carbon sink, absorbing CO2 directly from the atmosphere.
So what does this all mean when you combine the Kavach safety nets, the in-house manufacturing, the Robin Hood economics, the 99.6% electrification, and the solar panels? Where is this all heading? The sources paint this incredible, holistic, long-term vision. They talk about a future ecosystem that perfectly integrates solar power generation, deeply electrified railways, and localized electric vehicles.
It is the architectural blueprint for the ultimate sustainable transport loop.
Just visualize this future state for a second. You have massive solar farms generating power out in the rural plains of Rajasthan. That zero-carbon electricity feeds into the national grid. It powers a massive indigenous electric train that carries 2,000 people 500 kilometers across the country, affordably.
Right.
Those 2,000 people get off the train at a major metropolitan hub, and they transfer into electric buses, electric cars, electric two-wheelers, or electric bicycles to go that final last mile to their homes or offices. The entire journey, from the intercity trek to the front door, is powered entirely by the sun. There is no local exhaust, no reliance on imported oil, and an incredibly minimal carbon footprint.
And because of the sheer scale we discussed in Segment 1, when a system of this magnitude shifts toward that sustainable loop, the global environmental impact is highly measurable. We noted earlier that countries like Switzerland, Japan, France, and Germany have highly efficient, highly electrified rail systems.
Sure, but geographically and demographically, those nuggets are relatively small compared to the subcontinent.
Precisely. India stands out globally because of the intersection of three factors: a geographically massive network, extremely high passenger and freight volumes, and near-complete broad-gauge electrification. When Switzerland goes green, it is wonderful for Switzerland. When Indian Railways goes green, even modest improvements in efficiency produce massive environmental dividends at a global scale. It drastically lowers the baseline greenhouse gas emissions for over 1 billion people.
It is honestly breathtaking when you step back and look at the whole picture we painted today. We've gone on quite a journey through this data. We started by looking at a tiny colonial-era steam train chugging just 34 kilometers from Bombay to Thane in 1853. And we followed that technological and administrative evolution to a 68,500-kilometer electric juggernaut.
A highly complex system that manages to orchestrate the movement of 7.4 billion people annually on the back of automated AI safety grids, in-house hydrogen tech development, and a brilliant Robin Hood-style freight cross-subsidization model that ensures no citizen is left behind.
Right. It really redefines what is possible when you apply long-term vision to legacy infrastructure. To you, our listener, the next time you are sitting in highway traffic or paying an exorbitant fee for a short train ticket, or more importantly, the next time you hear a politician or a corporate executive talk about the fundamental impossibility of overhauling massive legacy infrastructure to make it green and affordable, you now have the ultimate counterexample loaded in your mental arsenal. You can point to 1.2 million people moving a mobile nation across the extremes of the Indian subcontinent every single day, running on a 99.6% electrified grid.
It conclusively proves that scale is not an excuse for bureaucratic stagnation. If engineered correctly, scale can actually be the very mechanism that drives revolutionary change.
Before we officially wrap up this deep dive, I want to toss it over to you one last time. Based on all the technical data, history, and economics we've unpacked today, what is one final, unscripted thought you want to leave ringing in the listener's ear?
It goes back to that concept of challenging what we accept as impossible. If a system as incredibly massive, as deeply historic, and as logistically chaotic as Indian railways can successfully pivot to 99.6% electrification, and if they can build automated safety tech and hydrogen trains while remaining affordable enough for the poorest citizens in a developing nation, what does that say about the excuses other global industries make?
That is a great point.
What does it say about the excuses other fully developed nations make regarding the impossibility or the prohibitive cost of going green at scale? I want the listener to consider what other legacy systems in our world, our national power grids, our global shipping supply chains, our urban housing models, could be entirely radically reinvented if we just applied this specific model of scale, self-reliance, and deliberate subsidization.
If they can figure out how to move the entire population of the Earth and go green while doing it, the rest of the world really is out of excuses. Thank you for joining us on this deep dive. Keep questioning the systems around you, and we will see you next time.